Hi everybody, this is example 11:16 and we're going to apply what we know about rotational work and rotational power to evidently making ice cream. All right, so we're told a bunch of things about making ice cream. I guess you have to turn this ice cream handle to kind of mix it up. I think you put obviously sugar and ice and cream in it, and I think some special kind of salt as well. But you have to have somebody that turns it or stirs it up. So a torque is required to do that. So let's write that down. Our torque is 5.7 Newton meters. All right. And then the question then is how much work. That's the question. By the way, I should be writing my W's more like W's and my omegas more like omegas. Work is the question, and we are given an angular displacement, that is one complete revolution of the handle. So our angular displacement is I'll just say one revolution, but of course we know one revolution equals 2 pi radians, and so that's really what it's going to be, 2 pi radians right there, okay? So part A, we want to find the work. Well, we just saw in our previous section as we derived a couple of equations, work is nothing more than torque times our angular displacement. This should be pretty, all right? So work equals torque times delta theta, and so in this case it's going to be 5.7 Newton meters times 2 pi radians right there. And I'm guessing it's going to be between 30 and 36. 5.7 times 2 pi, 35.8. 35.8. What? Well, it's joules, right? Joules. You could say Newton meter radians, I guess, but it's really, radian isn't exactly a unit, all right? So it's really just Newton meters or 35.8 joules. That's how much work is done in one complete revolution right there. All right, part B, we're asked about the power. All right, so power in part B, it's a capital P, that's not a lowercase p for momentum, but how much power is required to turn the handle if each revolution is completed in 1.5 seconds? All right, well, again, this is nothing new to us. We're just using new units. We have a pretty easy equation for this as well. Power is nothing more than work over time. All right, so we could say it's torque times angular displacement over time. We just have our work right here. Power equals work over change in time. So why don't we just substitute our work in? Now, if you were asked for power right at the very outset, you would just you would take your work and multiply the torque times the angular displacement. But we have our work already, so let's just put it in. 35.8 joules divided by how many seconds? 1.5 seconds divided by 1.5. I get 23.9. What is our unit for power? It's watts, right? W for watts. And I've never made homemade ice cream, but I'm told that it's a pretty labor-intensive process because you've got to put out a lot of watts of power to do it in a certain amount of time. Otherwise, it takes forever. So that's it. This was just an application of some pretty simple equations that we had derived in the previous section on rotational work and rotational power. But again, it should seem somewhat familiar to us, or easy even, because we've had this stuff before. We're just using new units, but it's really the same relationships between all of our values. All right. So let's go back to our example right here. That's it for example 11:16. Thanks for following along. Make sure you ask me if you have any questions, and see you on the next one.